we will go ahead and get started. So what we're going to do is finish up Chapter 4. I thought they fixed it. Whatever. We'll finish up Chapter 4. So you've got that homework that's posted. I've given you enough homework to probably get through all the material we're going to talk about today, and then hopefully I'll have more homework for tomorrow, which will cover some new stuff. So Thursday, we looked at atomic notation, how we end up representing individual elements. Okay, your textbook does refer to this as atomic notation. I think it's a little bit better to refer to it as nuclear notation. Why? What reference within that symbology tells you anything about the electrons? Nothing to tell you about the electrons in your atom. Okay? Which means we don't care about the electrons. All we're really focused on with this notation is just the nucleus. Okay? We can interpret some information about the electrons by taking a guess at it, but it turns out that notation really doesn't give us that information. Okay? Anybody that's seen some further information, where do we find information about the number of electrons? Could look at the number of protons, but that doesn't guarantee it. As we'll see later in the semester, upper right-hand corner tells us about our charge. That's going to give us information about the number of electrons within that individual molecule or element. Okay? And we will see that before exam 2. I don't know when exactly, but we'll see that come up pretty soon. Okay? Then we've got our periodic table, okay, which organized all of this information so that we could then find it and kind of look at a new organization for it. So we're used to seeing the periodic table in theory now at this point in the current format that we've dealt with, but that wasn't the original beginning point for it. Remember when we put up Dalton's old experiments or his notations for his theory, he only had to deal with something like 20 different elements, and he had a slightly different order than what we currently have. He didn't have it nice and shaped out. Okay, so where did this shape and organization come from? And that was ultimately trying to find different comparisons or patterns within the elements. Okay? Sorry, I thought we were there. We aren't there yet. We forgot to talk about isotopes. So when we looked at our notation, it gave us information about the protons. The protons do what? What information does that tell us? Okay, they define the element that we're going to be working with. So if you have 4 protons, you know the element you're looking at is beryllium. Okay? Or you could cheat and say Be. What happens when we look at the number of neutrons? Okay, that's really going to determine our mass for the individual elephant. It's early, right? Yes. Define our element. Sorry. Elephants were completely wrong. Elephants don't even rhyme with mass. Define our mass. Okay? Our protons and neutrons contribute, but our protons can't change once we're looking at an individual element. The number of neutrons can potentially change, and that's how our mass changes. Okay? The other thing we could look at is instead of looking at defining the mass for an individual element, we can then separate it into a different category, and we can look at it as defining what is known as the isotope. Okay? Your isotope is the same element, it just has differing numbers of neutrons. Since those neutrons don't contribute a charge, a lot of the chemistry of that element is the same. Right? It does change some minor effects, but for the most part, we see the same reactivity, we see sort of the same general properties for that compound or that element. So what's happening when we look at an isotope? All atoms, like we just discussed, have the same number of protons. Remember, our protons define the element. If we go through and look at the individual elements, though, particularly if we look at the molecular weights, or sorry, atomic weights of each of our elements, you'll notice that they don't come out to whole numbers. There is some variation off of the whole number. And when we're totaling, we're just looking at the number of protons and neutrons within it. So we should expect to see a whole number. And we don't for a lot of the elements. So why do we not see that whole number? That's because what we're reporting on our periodic tables is the average atomic weight for that particular element. Okay, so some elements have more neutrons or less neutrons. That changes the weight or our mass, and we end up getting a different massed element. To account for that weight, or to make sure that we report it, we show that in a weighted average that shows up on our periodic table. Yes?
Can that weight be electrons?
The electrons were what weight contribution? 1,827, yeah.
That's like,
If you add a lot, say like 100, you're now getting up close, not even close. If you added 100 electrons, okay, that's now 100 over 1,826. That's getting more, but it's not that big of a weight contribution. Okay, so even when we push up to the higher elements, the weight contribution of our electrons is still relatively minor. It does contribute if you shift out far enough decimal places. Okay, but in most cases that you guys are going to be working with this semester, the electrons don't contribute to it, the overall mass. So what we're concerned about are our protons and neutrons. So our isotopes are the same element, but have different masses because of differing amounts of neutrons in them. Okay? So one of the big classic examples, which is actually relevant for organic chemistry, we can look at hydrogen. Okay? The most common isotope for hydrogen is hydrogen 1. Any guesses why it might be hydrogen 1, how you might know that? It's the atomic weight of hydrogen reported as 1. Okay? Which means when we look at a weighted average, there's not a whole lot of something in there that has a higher atomic weight. Otherwise, when we looked at our average, it wouldn't be exactly 1. Okay? Turns out that we can add another neutron to a hydrogen element, or the hydrogen atom, and we can make it deuterium. Okay? It gets a special name in this case because it's commonly used, particularly in organic chemistry. So the more common isotopes that we have to work with as far as chemistry goes typically pick up an extra name. Okay? How else could we refer to it without having to know that extra name? Because that could be a bit tedious. Some of these have 2 or 3 different isotopes, and if we had to name all of the elements on here and then name all of their isotopes on top of it, that's going to be a lot of effort. How could we write it out so that we know what we're looking at? There's a couple big ways that we could do it. One, we could look at the symbols. Okay, and you'll notice what I've circled here is the mass. Bringing in that 2 now says we're looking at a different atomic mass for the hydrogen element. Okay, but if we had to then speak that to somebody, what do we say? 1 superscript H? Okay. Or superscript 2 H? It's a bit tedious to go through and say, so how could we actually refer to that mass? Well, it's our hydrogen element with mass 1, or our hydrogen element with mass 2. Okay. We typically don't refer to hydrogen 2 as hydrogen 2 because we have that other name for it, deuterium. Okay. Another common, or not common isotope, but another isotope of hydrogen. Any guesses? What do you think we could refer to it as? Let's add another neutron. There we go, hydrogen 3. Yes?
Sorry, stupid question.
Nope.
Your example, protinium or whatever, you got 1, hydrogen 1. I thought the mass number at the top included proton and neutron.
It does.
2-1 then?
It does. How many neutrons does a hydrogen atom have?
It has to have 1, right?
Hydrogen has 0 neutrons. A hydrogen atom does not have any neutrons. Deuterium has a neutron. Why did we add neutrons to begin with? Okay, neutrons contribute to the mass, but why did we need that mass in there? Remember, we said there was two reasons why we could postulate the existence of a neutron. Mass was one. What was the other reasoning? Repulsive forces within the nucleus. Okay, if we take a look at hydrogen, how many protons are there? One. What's the repulsive force within the nucleus? Is there any positive repulsion? No, there's nothing to repel against. Why do we need a neutron? You don't. Okay? What happens when we move up to helium? So now what happens when we move to helium, we now have two protons. What happens when we bring those positive charges very close to each other? They repel. We now need some kind of glue or neutral feature to keep those two positive charges connected to each other. How do we do that? Now we bring in the neutrons. Okay? And what you were talking about before, Thor, was that one-to-one relationship between protons and neutrons. That holds true for everything above hydrogen. And even then, once you get too far up, it starts to fall apart. Right? Because as we get further and further into our radioactive isotopes, we have to add more neutrons than we have protons because the proton repulsive forces start to contribute too much. Okay? So hydrogen, in its most common state, has no neutrons. It's just that proton. Okay? And officially an electron. When we move to deuterium, what's happened? How many protons do we have? Still one. Why only one? What happens if we made it two? We made it two. It's not the element. Okay? So it's still one proton. How do we get that mass of two? We have to add effectively the same mass as a proton without the charge. What do we do that with? A neutron. What happens when we move up to hydrogen 3? How many protons do we have? One. Has to be one. To make up the rest of that mass, what do we need? We need two neutrons. Yeah?
So every time you go up an isotope like that, all you're adding are neutrons.
All you add are neutrons.
Technically change the element we added the second.
Exactly right. If we change the number of protons, it's no longer hydrogen. We can only change the number of neutrons. So when you're moving within isotopes, the only thing changing within an isotope is the number of neutrons. Yes?
Is there a limit to the amount of neutrons you can add to?
Yes and no. So no, there's not a theoretical limit. We can jam in as many neutrons as possible. Yes, what ends up happening is eventually it decomposes and falls apart. And that's what accounts for the radioactive elements. We've got so many different things in there that eventually it just falls apart. Okay? Which is why, when we look at the isotopes for hydrogen, we only end up with really 3. Okay? We end up with our standard hydrogen 1, then we get hydrogen 2. Hydrogen 3 is pretty much the last one that I've ever heard of. And if we tried to jam in a 4th neutron, we probably could jam it in there, but then eventually it would quickly spit itself back out because there's no need for it. Okay? Any ideas on a name for hydrogen 3 other than hydrogen 3? Tri, because we're looking at a mass, a larger mass. Come on. We're looking at, oof. Anybody know how to spell that properly? Good, and then say that's right. Tritium. Okay, so we're looking at hydrogen 3. We've now added 2 neutrons to that structure. Okay? So our isotopes are just changing the number. Whoops. Don't look at that. How many protons and neutrons does an atom of lead-206 have? What's our first thing that we're going to have to do? Identify our element on the periodic table. Lead has what symbol? Okay. Where's the 206 go in our notation? 206. What's the last piece of information we would need? We need the number of protons. So our atomic number So we'd find lead on the periodic table. It's 82, which means the number of protons are careful. What says 207? So if we look at lead, there are two numbers up there, 82 and 207. What does 207 stand for? You'll notice we're writing them oddly here. 207, according to our key, represents the atomic weight, not the atomic number. The atomic number is your number of protons. Okay? So you'll notice, don't ask me why they swapped the order on them. Okay? But they did. Okay? So our number of protons is how many? To figure out our number of neutrons, neutrons plus protons equals 206. Neutrons plus 82 equals 206. Our neutrons equal 206 minus 82. It's a goofy looking 8, but it's an 8. Okay? Questions about that? Okay.
I'm sorry, so the bottom number you said was atomic weight?
So we've got to be careful when we're saying bottom and top. If we take a look at that element again, if I'm going to write out the atomic notation, I get PB 206, 82. In the atomic notation, what is 206? Our atomic mass. What's the 82? Our atomic number. When we shift to the periodic table, and we look at the numbers on our periodic table, so let's go ahead and draw this in. Here we're saying it's our box on our periodic table. We had lead in the middle. I don't know why I have to look it up, but I'm doing 82 and then 207.2. What's the number on the top? It's our atomic number. Okay? So top versus bottom you have to be careful with. Okay? The top in our atomic notation is our atomic mass. When looking at the periodic table, in most situations, your atomic mass is at the bottom of the symbol. Again, I have no idea why they do that. Okay? How can you make sure that you're comfortable with that? One, memorize the atomic notation. That format you will get directly tested on. The next part is how do you get that information from the periodic table? Well, potentially the periodic tables could change, so that can make it more difficult. Okay, but you know you need the atomic mass and the atomic number. Okay, so if you're looking at a new periodic table, how can you tell which one's which? Look at the key or the legend on the periodic table to give you that information. So in our case, we've got a key with bromine in it pointing to our atomic number and our atomic weight, okay, or our atomic mass. Okay, make sense? So be careful with how you're looking at that. Make sure you're watching out for those kind of simple mistakes. Next part of this is recognizing what happens when we look at our atomic weight on the periodic table. Okay, the atomic weight is not that whole number that we looked at with our isotopes. Okay, it's slightly different than that. For hydrogen, it's darn close to exactly 1, but it still says 1.01. We say, oh, that's just an estimation issue. That maybe is the contribution of the electron. It's not, but let's pretend it is. Okay. What happens when we move up to lead? We jump to lead, it's now 207.2. 0.2 is not 0.1. That's a pretty big jump there. Why is that happening? Okay, we haven't added enough electrons to make it a 0.2. Okay. Or for mercury, it says 0.59. How can we get that 0.59 contribution? Okay. Your periodic table does not give you the atomic weight or mass of an isotope. It gives you the atomic mass for the element. Okay. When we look at an individual sample for an element, some of it is one atomic weight, atomic weight, some of it is another, because you have differing neutrons within the same group of elements. Okay? Unless you go through and purify and separate the isotopes away from each other, okay, what you'd have to look at is an average molecular atomic weight. Okay? So what we'd be looking at is your simple versus weighted averages. Okay? Most people are comfortable with simple. Okay? If we've got two things, I'm not sure I can come up with a quick example like that. Simple average, we just look at the part over the total. Okay? When we look at a weighted average, we now have to take into consideration how much does that particular thing contribute. So when we look at grades, for instance, your homework contributes only 10% of the total points in your final grade. If we look at its current value as far as points, it's worth a little bit more than that. Okay? Because we're only looking at the total possible. We aren't looking at how much it's supposed to contribute. That's where our weighted averages come in. So if we take a look at, say, hydrogen, we have some elements, so our atomic mass. We have hydrogen with an atomic mass of, say, 1, but then we also have the atomic mass of deuterium and the atomic mass of tritium contributing to this. Okay, and we divide that by our total possible, or our 3. But within, say, 3 molecules, actually let's change that 3, let's make it 100. So let's take a look at a 100 atom sample. If we just look at the isotopes, 1, 2, and 3 as possibilities, what we're saying is that each of those is contributing equally to our total atomic mass. Turns out that's not the case. Okay? Within a sample that has 100 atoms, it's probably something on the order of 99 of them have an atomic mass of 1. Okay? After that, now we kind of run into problems because I said numbers instead of percentages. So let's say 98 have an atomic mass of 1. 1 has an atomic mass of 2. 1 has an atomic mass of 3. Now when we go through and calculate, we would get a much more accurate representation of the atomic mass of that whole solution. What we've done is looked at a weighted averages, or the percent contribution per each of those isotopes. All right? To go through and do this, let's see if we got an example here. If we wanted to figure out the average atomic mass for gallium. Okay, so what we want to do is the same general idea as we did before. Try and figure out what our atomic mass should come out to be. So first off, do we know what the answer is? It is 69.72. How do you know that? We'll say atomic mass. How do you know it's 69.72? It's what the periodic table tells you. Okay, so what we now have to do is see how that number was calculated. So what we would go through and do is look at our mass contributions. Okay, there's 2 isotopes, gallium-69 and gallium-71. Okay, gallium-69 contributes a mass of 68.926 AMUs. And our, what was the other one? 71 contributes 70.925. If we just looked at this as an average, and we now just divided by those 2 possible elements, do we get 69.72? Anybody do that calculation? So we want to add the 2 numbers first and then divide by 2. What do you guys get? Is it too early?
Oh, I did. Go ahead and book already.
You already did the averages?
Yeah.
70.4 something. That's not our atomic weight. So we've not calibrated appropriately. So what we need to go through and do is say that they aren't in there in equal amounts. Okay, to do that, what we effectively said was that 50% of the sample, 50% of it was that, and 50% was the other one. Okay, well, according to the information that we're given, is that true? No. We have to incorporate those correct percentages into this. How do we know it was 50% before? What's 1 divided by 2? 50%. There's where our 50s came from. So what we need to incorporate is the actual percentage compositions for each of these. For our 69, we're looking at 0.6011%. For our other one, 0.3989. Right? Yeah. When we go through and calculate that, the number we get, you had it, Nate, right? Yeah. Exactly. 69.72. Okay, so we've now accounted for that appropriately. So in trying to figure out your atomic mass for an individual element, you have to take into consideration the percent composition. How much of that is actually present within an individual sample. Okay. A standard average, as we looked at before, assumes that we have equal amounts for each, okay, which we can't do. Okay. Questions about that?
Do we have to divide by 2? Or?
We don't have to divide by 2. The dividing by 2 in the first case gets us effectively our percents. So if we take our, I'm just going to write 69. 69 plus 71 divided by 2 is the same as saying that I have 0.5% of our 69 one plus 0.5% of our 71. Okay, so we don't have to incorporate that division number because that's already involved in our percent calculation. All right, questions about that?
Did you say why it's AMU exactly?
I didn't, and there's some pseudo reasons behind that. I was wondering the same thing. Where did this AMU come from? Okay. Textbook just threw it in there. So I was wondering why it didn't show up. Our atomic mass unit is a way to represent the mass of an individual atom without having to look at the kilogram value. So I don't think I've got it on the slides. Anybody happen to remember the mass of a proton in kilograms? Nobody remembers. I'm just going to make up a number. It's like 1.71 times 10 to the negative 13th kilograms. Okay. If we added up a whole bunch of those, our number is going to be awful that we would have to report on the periodic table. We'd have this massive exponent number. Okay. That's a pain to work with. So what we go through and do instead is now say, well, an atomic mass unit is roughly 1.71 times 10 to the 13th kilograms. So what ends up happening is we can then go through and count based on the number of protons or the number of neutrons. Okay, so it helps simplify the mathematics. So it's an extra conversion factor, which I don't think the textbook has shown. Yes?
Do we need to memorize that?
That number in particular, no. Please, God, do not memorize that number. I just made that up. Okay.
It's 1.67, is that 24?
24. Since you've got it, I'll go ahead and write it up there. 6.7 times 10 to the negative 24th. Okay, that one's a little bit more appropriate. Okay, so now if we took up all of our protons and added them up, we could get our mass in kilograms. That number is ridiculously small. We could even convert it into grams. It's still going to be ridiculously small. If we wanted to report that on our periodic table, that's going to be a pain to write out for every single one of the elements. So what we've done is further convert it into what's known as AMUs. A for atomic, because we're looking at the atom. M, mass. U, units. Okay? So we effectively invented our own mass unit for this particular issue of looking at just an individual atom. Okay? So that's where the AMU comes from. It is convertible into kilograms if you so desired. We will probably end up looking at that later in the semester. And we'll get rid of the AMU altogether and convert it into something altogether much more useful, again, later in the semester. All right. Some connections that we could draw on here, since they mentioned it. you can look at something known as heavy water. Okay? All that's happened is that we've taken the same compound, it's still water, still has hydrogen and oxygen in it, except we've added neutrons. And in particular, when we're looking at heavy water, we've added neutrons to the hydrogen atoms to make deuterium oxide. Okay? So what's happened if we look at our formula? Because remember, deuterium is one of those common ones that we've used a lot. Instead of referring to it as hydrogen 2, they gave it a new symbol, D. So when we look at the water, or the formula for heavy water, it's going to be D2O, because there's 2 deuterium atoms per oxygen to generate our water. Okay. It's called heavy water because it's got a heavier mass. Okay. So it does change some of the properties of water. They do use it apparently in nuclear reactors, slow down neutrons being released during the fission process. Okay. I don't know. So, any questions on that? Just kind of a neat, pseudo-neat application to this. Okay, so now what we're going to do is jump to Chapter 5. And that is because the next section in Chapter 4 is looking at waves and light and particles, and starts to get all kind of loopy weird. Though thankfully we don't have to go into a lot of the mathematics, which you could look as a plus or a minus in that case, because you don't get the explanations on where these things are coming from. You just get told what they are. So Chapter 5, what we're going to do is look at the periodic table. Now that we have some idea of what we have as far as elements, we now want to try and organize those elements into some fashion. That's already been done for us in the periodic table. But when we go back in time, that wasn't already built for us. Okay, so there's some history, and I'm going to apologize in this case. I have not had time to make my own slides. So what I've done is cut and paste the textbook lecture slides around to kind of condense them and organize it a little bit better. But as far as at least the history goes, it's pretty much just what the textbook is telling you. Okay? So in 1829, that guy with a D, JWD, went through and observed that elements had different repeating patterns. Okay? At that point in time, we didn't have a lot of elements to look at. Probably only had 20. So when he went through and started to compare what he knew about the different elements that they did have, he started to notice some patterns within it. Okay? And those patterns he saw happening in groups of 3. So he started to classify the elements that they had as far in triads. Okay? If we take a look at our final periodic table, do we see any groups of 3? Nope. So, not a bad theory, but wrong. So we try again. 1865, this will be fun, Jar Newlands suggested the elements be grouped according to 7s, according to their atomic mass. Interestingly enough, no one believed him. But he actually had, at that point in time, probably one of the most accurate, and it's actually something that's really, really close to what we have now. Called it the law of octaves, so I don't know why they refer it as groups of 7. It's really groups of 8. What he was saying is every 8th element repeats. Okay, so some of the properties start to cycle over. So as we move across the periodic table, okay, we could see hydrogen to helium. We could see those properties being different. If we then do lithium and compare within that row of our periodic table, the properties are slightly different. But what he did notice is that when you get down to sodium, the properties of sodium were very similar to those of lithium, but not so similar to all the other elements. Okay, so what they were trying to do is look at tables of physical properties. Okay, densities, boiling points, melting points, solubilities, and looking at those and trying to group elements in the periodic table according to those properties. Okay? What made it more difficult? They didn't have all of the elements. Okay? But some of their patterns that they picked up allowed them to be able to predict new elements. Say, hey, there should be an element here because I know what's above it and I know what's underneath it. Okay? So there has to be some intermediary element that we haven't yet discovered. So it was kind of neat as far as discovering new elements and trying to theorize new ones as well. Yes?
These historical, the German side, whatever, Dobermeyer, do we have to memorize that stuff for a test?
As far as the periodic table goes, no. The one name that I do highly recommend you memorize will be Mendeleev, because he's considered the father of the periodic table. Okay, so his name is important. The first two guys, I will not test you on that, particularly because I can't say their names. If I can't say their names, it's probably a good estimate that I won't test you on it. Okay? But that brings up an interesting point about the history that we talked about on Thursday. Okay? We did mention a couple names then. Anybody remember those names? Dalton, Thompson, Millikan. Mentioned Curie, and I'm running out of fingers, Rutherford. All 5 of those names are important names. You do need to know those names. Okay? Those were the ones that actually led us to our understanding of an individual atom. These guys were just trying to organize the periodic table and were wrong. If they're wrong, typically not a good name to memorize. Okay? Mendeleev came along and went through and started to organize the elements according to their atomic mass, which also turns out to be wrong. But if you go through and look at our current periodic table and compare how they're organized, they are set up via atomic number. But if you go back and compare atomic mass, holds pretty true. Hydrogen with atomic mass of 1. Helium, 4. It's bigger. What about lithium? Bigger still. Beryllium, still bigger. So the atomic mass does translate fairly closely to the atomic number. Because the mass was easier to grasp. Okay, why might it be easier to grasp? Did we have an idea of the number of protons and neutrons at that point? We're looking at, it's actually interesting that 1865 he came up with this. Oh, that's still atomic mass. Why do we not associate it at this point according to atomic number? What did atomic number tell us? Protons and neutrons. When did we know that we had protons? 19th century. There's no way that they would be able to organize these according to their atomic mass, or sorry, our atomic number, because they didn't even think there was something smaller than an atom. So you can't make that comparison for them. The only thing that they really had to be able to measure would be the mass of those particles. Okay, so they're looking at the mass, not the number. So he went through and organized it according to atomic mass. And he kind of did the best organization he could do, and he took it a step further and was able to actually predict new elements. Okay, the big ones are labeled with the eka in this, are labeled with eka in the middle. See, am I still drawing? Yeah. Okay. Anybody know what eka stands for? I think he was Russian. Nobody knows what eka means. Okay, it means like. So what he was saying is that this is eka aluminum. Whatever this element is similar to aluminum. Whatever this element is similar to what's above it. Okay, so that eka prefix, he was just guessing. He didn't have an element to put in there, so he just took a guess and said it had to be similar towards the previous element. Again, eka, I have no idea what that means. I did just make that up too. Okay. And so that's where he was able to predict these new elements. So what he went through and did is took a look at silicon, and he knew that there was some element underneath it. Okay? And this is where he called it eka silicon, similar to silicon. And he had a list of all of those properties. Okay? It was gray. He knew the weight. He knew the density. He knew the melting point. Okay? He knew how it would react with oxygen. He just couldn't predict or hadn't actually discovered it yet. Okay? Give it, what is that, 18 years later? 17, 16? A number less than 20 years later? They end up discovering germanium. Where's germanium on the periodic table? Directly underneath silicon. He was able to predict the properties of that element based on the other information that he knew from the other elements. Okay? He got colors, he got weights, right? He got densities. What they were doing is just predicting based on current patterns. Okay? So it's actually kind of neat to be able to do that.
So did he get the credit for it though, even though he didn't name it?
Oh darn, I thought I had another slide in here. For germanium, did he get the credit for discovering it? Probably not. Yeah.
Why would you do all that work for nothing to get?
So, well, he got credit for plenty of other things. He got
Right.
credit for determining the periodic table and organizing it into a fashion where you could predict it, which is pretty huge. If you take a look at the discovery of the neutron, who got credit for the discovery of the neutron? Chadwick, I think, was his name. It's somewhere in the slides. Rutherford was the one that predicted that it should exist. He didn't actually find it, though. Okay? So he's tied in as potentially a footnote, saying he provided the information that allowed for somebody else to discover it. Okay? Same kind of thing is happening here. Though, in defense of Mendeleev in this case, who did discover germanium? Good call. Probably some German. The name associated with it?
Yeah.
Whose name is associated with it? Mendeleev. Okay? So just because you discover something doesn't mean that you necessarily get the, the historic popularity of it. Okay? So there's some kind of interesting history behind building that. I would recommend you read up on it in the textbook. You can expect, I really thought I had another slide in here. I must have accidentally deleted it. The textbook, I'm pretty sure, will go through and list, at least in the homework, a couple properties, okay, before and after an unknown element. And you would be expected to predict the properties of the unknown element. Okay, how would you do that? Well, if you know the atomic mass of the one above it is 15 and the one below it is 20, what should the one in between be? Somewhere in between 15 and 20. Okay? So use that information to kind of pick your middle ground and decide what's going on. That's how he was able to predict the properties of germanium. Okay? Other things that you could see, who's the father of the current periodic table? Mendeleev. Okay? So kind of simple approaches to this kind of material, kind of historical facts, and then given a bunch of data, can you analyze it and come up with effectively educated guesses about those new materials. Okay? After that, we can start to look at some classifications within your periodic table. The inert noble gases were discovered, where is that? In 1894. And they discovered that, I think, with argon. I thought I read that somewhere. Why would they get called inert or noble gases? What does inert mean? Not active. Inert means it doesn't react. So one of the things that's interesting about our noble gases, or the inert gases, so you're looking at the far right of your periodic table, starting with helium, working down to neon, argon, krypton, xenon, and radon. Okay. All of those elements, okay, when they were first discovered, they could not get them to react with anything. Okay, the most common thing to react species with was oxygen. Okay, they could not make a compound with those elements in oxygen. It just was physically impossible. Because they did not react, we called them inert. Okay? We've since adapted that a little bit because inert's a funny word. We came up with another word, noble. What is noble referring to? It's the uber rich, hoity-toity. Not going to interact with anybody at all. I'm just going to drink my tea. Okay? The British. There we go. Blame it on the British. Okay? We're looking at the noble gases in that respect. They just really don't react very well with anything. Okay? You'll notice at the end of that I said very well. Okay? For the most part, those compounds are fairly unreactive. It turns out as we get them big enough, okay, how do they get bigger? How does any element get bigger? Okay, neutrons changes the mass, but what happens is we go from, say, argon to krypton. What would you predict about size? We haven't discussed this yet, but see what you can come up with. Why would it be bigger as we go from argon to krypton? Why would krypton be bigger? Sorry. There's more protons. There's more electrons. There's more of everything in it. What happens when you eat more? You get bigger. Okay? Same thing's happening with your periodic table. The more protons and electrons and neutrons you put into it, the bigger it gets. Okay? What ends up happening is the larger you get, the electrons on the outside of that atom start to become more reactive. So if we get big enough into that xenon and krypton area, we can actually force those molecules or those atoms to react with other species. They're very difficult reactions, or relatively difficult reactions to run. We do kind of have to force it to occur. Okay? So officially, the noble gases aren't completely inert, which is why we typically don't refer to them as inert anymore. We look at them more as the noble gas classification. They're difficult to get to interact with anything else. Okay? Periodic law. So now what we're doing is starting to look at our periodic table. Okay? The properties of our elements recur in repeating pattern. Okay? This is ultimately what Mendeleev was looking at. If we look at individual periods, period on the periodic table is which direction? Row or column? Okay? We're saying it's periodic law, and the properties of the elements in an individual period have very similar chemical properties. Okay? When we talked about the reactivity of lithium, we compared it to what? Reactivity of sodium or potassium. Where are those elements? In a column. Your period is looking within an individual column. Okay? So our periodic law is stating that the properties of elements within that column all have very similar properties. How do we decide where those periods are? That's based on increasing atomic number. Okay? When do we decide to loop back and start repeating within an individual period? There's two approaches to that. One, you test it and found out, oh, it reacts the same. There it goes, must be there. Okay. The other option is that you have to have some understanding of how an atom was built. Okay, what's going on with increasing atomic number? Okay, which is looking at the wave properties for light. Okay, so we haven't quite covered that yet. Okay, so that's the next sentence here, looking at Niels Bohr. Niels Bohr was able to really finally put the nail in the coffin and get us set up with the periodic table that we have today, because he was able to predict what's changing as we move through the periodic table and what's accounting for those physical properties. Turns out it's not the nucleus, it's the electrons. Okay? How those electrons interact with other particles or other atoms is what's determining a lot of the reactivity and the patterns that we see within the periodic table. Okay? And a lot of the groupings that are technically up there. So we will come back to that once we talk about Niels Bohr, but that's going to be a little ways out. So there's some other things that we can look at. Did I really label that wrong? So apparently I misspoke about periods. You guys were right, or at least a few of you were right, saying we're in a horizontal row. I'm not quite sure I liked how that previous sentence was phrased then. So a vertical column, we're looking at a group or a family. Within a group or a family, we get very similar chemistry. Okay? Lithium will respond the same as sodium, okay? Same as potassium. So the chemistry within an individual family or group, our vertical column, is going to set us up with similar chemistries. Okay? So we get repetitive chemistries along that direction. When we look at a horizontal row, that's where we're looking at our period or series. The chemical properties change pretty drastically along that. Okay, do we have any evidence or proof of that? beryllium metallic or not metallic? How do we determine metallic versus not metallic?
It's in the middle.
We could look at physical properties, or we look at our periodic table and we notice, what was this bolded line going downwards a representation of? The semimetals were on that line. To be a semimetal, you need to be transitioning between metals and nonmetals. When we move across a period, okay, what happens? Beryllium is a metal. Boron, nonmetal. Okay, that's a gray area one, so let's push to carbon. What's carbon? Nonmetal. Nitrogen. Okay, nonmetal. What's going on? Within a period, what happens to the chemistry? Does that change? Yeah, that changes a lot. Okay, so it's within the column that we get very similar chemistry. Across a row, okay, or within allegedly the period, the chemistry changes rather drastically. Okay, is that what that last slide said? Did I just misread it? Oh, that's what I misread. This says periodic law is not referring to a period. It's saying that there are repeating patterns. Periodic, in this case, does not refer to a period. Okay, I know that's kind of an odd statement to make, but that's the mistake that I made. Okay? So your periods are, by definition, your rows. Your groups are your columns. Within a row, your chemistry can change quite substantially. Within a column, the chemistry stays virtually identical. Okay? Questions about that? Because I know I goofed it. We're 40, right? Okay. Well, I can't forget that.
Every class. It's funny to me.
I have like 6 classes. Give me a break. Okay. Some extra information that we could add in here just to have people memorize stuff. That said, as far as a test question goes, what I might ask is which of the following are not a family name, and then might throw goats in there. Okay. So these are your common names for individual families, okay, or groups, so individual columns. If we take a look at group 1, you'll notice that there is some interesting phrasing here. Group 1, 2, 15, 16, 17, 18. Where are those numbers coming from? Group 1 starts with what element as an example? I've actually listed it up on the whatever that is, the slides. Lithium. Did not include hydrogen for a very interesting reason, which we'll talk about later. Okay, take a look at lithium. Okay, group 1, lithium is in which column? Why do we call that the first column and not the last column? We read left to right. Okay, group 2, our alkaline earth metals start with beryllium. Where's beryllium? The next column, what number precedes? Follows 1. 2, oh, interesting. Okay. The next group, the pnictogens. I just like to say that. It's just a fun word. You should try and say it too. Ready? 1, 2, 3. See? It's kind of fun, isn't it? Starts with nitrogen. In group 15, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, look at that. 15. There's our nitrogen. What are those numbers referring to? Each column on the periodic table. There is some slight debate over what those columns should be referred to. A lot of that is just historical. Your textbook talks about that a little bit. I think what they've settled on is IUPAC just numbering them all the way straight across. So you get 1 through 18. There are other numbering systems, which if you look at the top of each of those columns, you'll see some of those numbering systems. You see some Roman numerals, you see some A's, some B's. Pretty much all those are just confusing and not really all that helpful. Okay? Same with these numbers and even these names. Okay? Group 16, starting off with oxygen, are referred to your chalcogens. It's also a fun one. Group 17 are your halogens, and we already talked about group 18, our noble gases. Okay? So one thing that's nice about column 18, you notice that we actually added some information in that name. What information did we add? They're all gases. We provided some information about the phase and their reactivity because they're noble. You know, the pinky and T, right? Okay. Everything else within each of those columns, you end up seeing similar chemistry. One that will show up repeatedly. Did I say that right? Repeatedly? Repeatedly? Okay. Your halogens, the name for that individual column, your halogens, will show up again and again and again. That one I will ask you to memorize. You need to know what your halogens are, what column that's referring to. That's everything underneath fluorine. Fluorine, chlorine, bromine, iodine, astatine. Oh, good question. Does it translate all the way down into these guys? Okay, what do you guys think? Does that column apply all the way in?
Yes.
Okay, it's a no. Why no?
Because it's over here.
Okay. One thing you can look at for a no, there's a big gap between those two. When we look at 85, 117 to 70, look at the gap. Okay, it is broken off of the periodic table. The reason it's broken off is that those two last column or rows are actually supposed to slide into the very middle of the periodic table. Very, very rarely do you see your periodic table with those two rows slid in there. Why? It makes it really, really long. Extends it out a huge way. So instead of having nice 18 rows, you don't get the 18 rows. Okay? These elements, because I don't think I've actually listed it on the slides, are known as your inner transition elements. Yeah, let's go ahead and talk about that. Let's list this. A couple extra rows that we can add in here, or groups. Group 3 to 12 are referred to as, anybody know? Your transition metals. Why transition metals? What's happening as we move from our metals to, it's transitioning towards our nonmetals. So there's our transition metals in that inner table. Okay? In the now exterior section of it, I'm not even quite sure how to number those. Let's say elements. We got 57 to 71 and 89 to 103. 57 to 71 are typically referred to as the lanthanides, which I'm probably butchering the spelling on. The 89 to 103 are referred to as the actinides. Why? Element 57 is known as... No one memorized that? Lanthium, hence everything after it, the lanthanides. Element 89, actinium, hence actinides. Did I say that wrong? Okay. As a group, those are known as the inner transition metals. Okay. Typically don't hear much talked about as far as those go because they tend to be radioactive and not anything that you guys can deal with in the lab. Okay, so we kind of just leave them alone. Okay. Some periodic trends that we want to look at here. There's a couple trends that we want to evaluate. We can look at atomic radii, so how big an individual element is. Okay, if we take a look at our atomic radius, I really don't like how they've got this phrased. As we add elements, or add, we're going to do this. No, we're just going to have to memorize it at this point. We'll discuss it once we get a little bit more on atomic structure. We take a look at our atomic radius. When we go down a column, what's happening? We're adding more protons, more electrons, more neutrons. The mass increases, which means what happens to the size? It gets bigger. The more things you put in it, the bigger it gets. So when we look down a column, at this stage, that's a relatively easy one to see. Okay? We'll see it get bigger. What they've gone through and phrased is looked at the negative. Okay? What happens to your atomic radius? As you go up a group, okay, it's going to get smaller. Okay? The tricky one that's going to involve knowing a little bit more about atomic structure is looking at the atomic radius, within a period, okay, across a row. What happens as we go left to right? Okay, initially, what might we predict as we go from lithium to beryllium to boron to carbon, nitrogen, oxygen, fluorine? We would predict it to go bigger. Why? The atomic mass is getting bigger. We're adding more protons, neutrons, electrons. What actually happens to it? It decreases. Okay? So we must be missing some information about how elements are put together. It's not just putting in a bunch of protons, neutrons, and electrons, but it's where do those protons, neutrons, and electrons go that are going to contribute to your radius. Okay? Which of those three subatomic particles do you think are going to contribute most to the radius? Protons, neutrons, or electrons? Tricky concept. How about the protons and neutrons? Where do they exist? In the nucleus. As we add more, yes, we would expect the nucleus to get bigger. We look at an atom, okay? And we said if we took the nucleus of an atom and we made it the size of a marble, what was the size of the atom? Superdome. Okay? Our protons and neutrons were all crammed into a marble. Yet the size of the atom was much, much larger. What's contributing to the size of an individual atom? Is it the protons and neutrons? No. It's the one particle that we haven't really addressed. That's your electrons. So where the electrons are located around the nucleus is what's going to contribute to our atomic radii. As we move down a column, I can't say that yet. As we move down a column, we're adding in a lot more electrons. As we move across a row, it turns out we're adding those electrons into effectively the same space, which means we don't increase the size. If anything, it actually shrinks a little bit. Okay? And we will talk about that once we get a better understanding of what makes up our electron clouds. Okay? So we've got a pictorial image looking at your atomic radii. I'm pretty sure that's pretty much the end of what I wanted to talk about. And we're going to shift back to Chapter 4 on Thursday. Okay? And we'll get a look at atomic structure.